This common degradation is mostly due to a process called electrochemical corrosion, which is fundamentally driven by chemical reactions. Think of it like a tiny, destructive battery forming right on the surface of your material. Metals naturally seek stability, which means they want to revert back to the oxidized state found in their original ores. This process requires 4 key components to be present in a localized corrosion cell. First, we need an anode, which is simply the spot where the metal begins to give up its electrons through oxidation. At this anodic site, the metal atoms dissolve into the environment as positively charged ions, essentially weakening the structure. Next, we need a cathode, which is the opposite location where those released electrons are accepted or consumed. The most common electron acceptor in atmospheric conditions is dissolved oxygen reacting with water molecules. The third necessary element is the electrolyte, which is the conductive path facilitating ion movement. This electrolyte is often just a thin film of moisture on the metal's surface containing dissolved salts or acids. Finally, a metallic connection allows the electrons to physically travel from the anode to the cathode area. When iron corrodes, we call this specific process rusting, which is a textbook example of this electrochemical behavior. The resulting iron ions combine with oxygen and water to form the familiar flaky reddish-brown iron oxide we know as rust. Interestingly, when 2 different metals touch in an electrolyte, one corrodes much faster in a process called galvanic corrosion. The more active metal sacrifices itself to protect the less active one, illustrating the principle in action. Understanding these fundamental anode and cathode reactions is crucial because corrosion costs industries billions annually. By controlling the presence of water, oxygen, or by applying protective coatings, we can successfully interrupt this spontaneous reaction.